Adversarial learning for medical visual question answering. Medical visual question answering is a system that takes medical image and a question that are related to each other, and this model is expected to predict the answer to this given question. Basic VQA model. This model takes an image and a question as inputs, and the feature extraction modules extract the image and question features. The image question correlation generator is responsible for generating the image question embedding. And the answer prediction module is responsible for predicting the answer. But the problem is that this image question embedding is smaller in size when compared with the original image and question encodings. This means that the image question embedding only contains less information than the originals. So, this may result in losing the required answer-related information that needs to predict the answer. Therefore, the VQA model would not be able to correctly predict the answer. In a VQA task, learning this joint representation is a challenging task, because of this reason. The most common approach in VQA models to learn image question embedding is the multimodal correlation. To learn the joint representation properly, the most known approaches focus on studying the multimodal correlation between the question and the image. That is, giving more attention to the objects or the regions in the image that are in the question. You can see two examples here. In the first example, the question is what is the color of the bird? Then to find the answer from the image, the system can give attention to the region where the bird is located. But, when the question does not contain any clue about the image regions, the image question embedding may not contain any answer-related information, so the joint embedding may not be able to predict the correct answer. The problem is that these types of data are common in the medical domain. As you can see in the two examples below. Project objectives. Observe the possibility of using the question-answer embedding as an ideal embedding to infer the answer-related information. Use a generative adversarial network to enhance image question joint embedding of a medical VQA model. Compare the performance of the novel method against the baseline. Solution. This is the solution architecture of our solution. Our module consists of four main components. 1. Question-answer embedding generator. 2. Question-image embedding generator. 3. Discriminator module. 4. Answer prediction module. We will look at these components separately. Our methodology consists of three phases. Phase 1. Train the question-answer embedding generator using questions and answers and evaluate the performance. Phase 2. Train the question-image embedding generator using adversarial learning. Phase 3. Use the question-image embedding generator trained in Phase 2, and train the answer prediction module. Phase 1. Question-answer embedding generator. For the adversarial learning approach, we need a question-answer embedding generator to generate a question-answer embedding. In this phase, we implemented a question-answer embedding generator using the self-language attention layers in a model called LXMERT model. Then we trained the generator. For each question-answer pair, concatenate the answer and question and input that into the generator. Then question-answer embedding output, feed into the answer prediction module and predict the answer. After that we check the performance of the generator. Because we need to check, this question-answer embedding is good enough to use as an ideal embedding. As we expected, performance was greatly increased. That was expected because the answer features are already available in the embeddings. Results are available in next slide. After that, the question-answer embedding generator is saved to use in the next phases. This table shows the validation results of the question-answer embedding generator. This is where the component trained in Phase 1 is located in the full system architecture. Phase 2 – Adversarial learning. In this phase, we extend the pipeline to use generative adversarial learning. We created a fully connected neural network as the discriminator. Discriminator uses the output from the question-answer embedding generator trained in Phase 1 as the ground truth. Discriminator tries to classify two embedding correctly and adversarial losses feedback into the question image embedding generator. This is the architecture for Phase 2. As you can see in the diagram, discriminator feedback adversarial loss into the cross-modality encoder in the question image embedding generator. Then cross-modality encoder improved to output a better question image embedding. This concept is called as generative adversarial learning. This is where the component trained in Phase 2 is located in the full system architecture. Phase 3 – Answer prediction. In this phase, we trained the answer prediction module to predict the answer. Improved question image embedding generator used to generate the new embedding and input the embedding into the answer prediction module. This is where the component trained in Phase 3 is located in the full system architecture. This table shows the performance comparison between the baseline model and the improved model for each question type. After analyzing the dataset, we identified that there are some infrequent answers also. Therefore, we removed those low-frequency answers from our datasets and selected 85 frequent answers. After training the model with these selected answers, we could improve the accuracy of our model as shown in this table.